For eons, humanity has gazed upon the red planet, a familiar beacon of rusted desolation in our night sky. We see a world of frozen deserts, thin air, and a perpetual chill. Yet, beneath this seemingly unchanging facade lies a profound 4-billion-year-old mystery, a cosmic crime scene that holds the key to the very possibility of life beyond Earth. This is not simply a search for water, though water's presence is vital. This is the story of a great Martian heist, the planetary-scale disappearance of an entire ocean of air. Unraveling this enigma, we journey back in time to an early Mars that would shock anyone familiar with its current barren state. This was a world not unlike our own, swaddled in a thick, warm blanket of air, an atmosphere likely denser, even, than Earth's today. Under this protective canopy, liquid water flowed freely, pooling into vast, ancient oceans and carving the intricate, sinuous valleys that are still visible from orbit. This vision of a once habitable Mars is far from mere speculation. It is a narrative strongly supported by the precise geological evidence meticulously gathered by our tireless robotic explorers, rovers like Curiosity and Perseverance, whose wheels have traversed the very ground where these ancient rivers once ran. The central culprit in this immense atmospheric theft is none other than our star, the Sun itself. Its relentless solar wind, a supersonic stream of charged particles traveling at speeds of over 1,600,000 kilometers per hour, has been relentlessly sandblasting Mars for eons. To grasp the ferocity of this unseen attack, consider this. Unlike our Earth, which is shielded by a powerful global magnetic field generated by its churning molten core, Mars tells a different, tragic tale. Billions of years ago, the red planet's internal dynamo sputtered and died, its core solidifying, leaving it naked, exposed, and utterly vulnerable to the Sun's furious assault. To understand the mechanics of this ongoing robbery, we turn to the groundbreaking data from NASA's Mars Atmosphere and Volatile Evolution mission, known by its acronym MAVEN. Since its arrival in orbit around Mars in 2014, this sophisticated spacecraft, led by principal investigator Bruce Jakosky from the University of Colorado, has been precisely measuring the rate at which precious gases are stripped from Mars's upper atmosphere. MAVEN's instruments, designed with unparalleled sensitivity, have caught the solar wind in the very act, revealing the primary, insidious mechanisms of this atmospheric escape, a process called sputtering, where energetic particles directly knock atoms into space, ion pickup, where atmospheric particles become ionized and are swept away by the solar wind's magnetic field, and polar plumes, violent eruptions of gas from the planet's upper atmosphere. This planetary desiccation is no gentle leak. It is a violent, ongoing robbery, siphoning off the equivalent of a quarter-pound of atmosphere every single second. To put that into perspective, that is the weight of a small stick of butter, constantly, relentlessly, disappearing into the void, second after second, day after day, for billions of years. We can visualize this invisible war, an unseen struggle where the solar wind's magnetic field drapes itself around Mars, creating an induced magnetosphere that acts as a funnel, sweeping atmospheric ions away into the chilling depths of deep space. This ancient planetary catastrophe, this unimaginable loss, frames our present-day search for life on Mars in an entirely new light. It is not a simple hunt for microbes splashing in surface water. It transforms into a search for tenacious survivors, organisms that might have endured in the ruins of a lost world. Perhaps, driven deep underground, they found refuge where they could be shielded from the harsh reality of Mars's current, naked state. The question then becomes not whether life ever existed, but whether anything could have possibly survived such an epic, devastating loss. Our eyes are perhaps the most powerful, yet most deceptive, instruments we possess in the search for life beyond Earth. For generations, the human mind has projected its own hopes, fears, and familiar patterns onto the enigmatic red orb hanging in our night sky. This psychological phenomenon, a deep-seated tendency to perceive meaningful images in random or ambiguous visual stimuli, is called pareidolia. It is a fundamental aspect of human cognition, a survival mechanism that helps us recognize faces in the crowd or predators in the shadows, but it can also lead us down entirely illusory paths when turned toward the vast, empty canvas of the cosmos. To truly understand this profound impact on our quest, we must travel back in time, to the late 19th century, to the private observatory of Percival Lowell. He was an affluent American astronomer, driven by an almost obsessive passion for Mars. Lowell's fervor ignited after Giovanni Schiaparelli's observation in 1877 of what the Italian astronomer called canali, an Italian word meaning natural channels or grooves. Yet, through a fateful mistranslation, perhaps fueled by the prevailing Victorian fascination with exploration and engineering, canali became canals in English. This simple linguistic twist transformed faint surface features into the unmistakable hallmarks of an advanced, intelligent civilization. Lowell, telescope fixed on Mars from his Arizona perch, spent decades meticulously mapping these supposed conduits. His exquisitely detailed maps, published between the 1890s and the early 1900s, depicted an intricate, planet-wide irrigation system. He was convinced this was the desperate work of a dying Martian civilization, struggling to transport water from their polar ice caps to their parched equatorial regions. This was not merely a scientific blunder. It stands as a monumental case study in pareidolia. Lowell was not simply seeing, he was perceiving, interpreting subtle light and shadow variations as proof of a grand, planetary effort. Despite their complete lack of scientific basis, Lowell's theories resonated deeply with the public imagination, directly influencing literary giants like Howard George Wells, whose classic War of the Worlds brought Martians to Earth with terrifying realism. This captivating blend of science and fiction, in turn, fueled public support for the very space programs that would, decades later, send probes to Mars and definitively disprove Lowell's fantastical canals, leap forward to the modern era, and this ghost in the machine of human perception persists even with our most advanced technology. One of the most famous examples emerged in 1976, when the Viking 1 orbiter captured an image of a Martian mesa. From a specific angle of sunlight, the formation appeared eerily like a human face, with discernible eyes, nose, and mouth. The face on Mars quickly became a cultural phenomenon, a beacon for fringe theories and alien enthusiasts. Later, higher-resolution images from subsequent missions revealed it to be nothing more than a natural geological formation, a trick of light and shadow, yet the image remains etched in collective memory. More recently, the sharp eyes of online enthusiasts sifting through millions of images beamed back by rovers like Curiosity and Perseverance have spotted objects that resemble spoons, thigh bones, and even doorways on the Martian surface. Each time, the scientific explanation points to natural rock formations, carved by eons of wind and erosion. Yet the human mind's insatiable desire to find familiarity in the unknown continues to drive these discoveries. This historical human tendency to see what we want to see now presents a unique and profound challenge for today's astrobiologists. They are sifting through petabytes of data, a staggering volume of information equivalent to hundreds of thousands of high-definition movies, from missions like the European Space Agency's Rosalind Franklin rover and NASA's Perseverance. To manage this influx, scientists at institutions like NASA's Jet Propulsion Laboratory are developing and actively training sophisticated artificial intelligence algorithms. These machine learning models are designed to identify potential biosignatures, subtle chemical or geological indicators of past or present life. The irony, however, is that while these AIs are meant to be objective, the very humans training them carry their own cognitive biases. The critical task is to prevent these advanced algorithms from inheriting our human tendency towards pareidolia, to ensure they do not engage in a form of digital pareidolia, where the AI itself begins to see patterns that are not truly there. It is a delicate balance, a constant vigilance, to ensure that the first definitive sign of alien life we find is truly alien, undeniably distinct, and not merely another reflection of ourselves staring back from the desolate Martian landscape. The stakes are immense. The search for life on Mars is as much a test of our technology and scientific rigor as it is a mirror reflecting the deepest workings of the human mind. What if the ultimate clue to alien life isn't found light years away, but buried deep within the most hostile, seemingly barren corners of our own world? For generations, our search for extraterrestrial biology has been constrained by a very Earth-centric view of what life fundamentally requires. We seek water, carbon, and the familiar building blocks of deoxyribonucleic acid and proteins. But to truly prepare for the possibility of a unique, un-Earth-like biology on Mars, we must first confront a radical notion that life itself may be far more diverse, more fundamentally strange than we ever dared to imagine. This leads us to the concept of a shadow biosphere, a hypothetical microbial realm on Earth that might share our environment, yet operates with an entirely different biochemical rulebook. To redefine the boundaries of existence, we embark on a planetary journey without ever leaving our home world, venturing into places that are Earth's own hidden Mars. Our first stop takes us to the Atacama Desert in Chile, a place so parched, so utterly devoid of consistent rainfall, that it is considered the driest non-polar desert on our planet. For millions of years, vast stretches of the Atacama have received less than 15 millimeters of precipitation annually, an amount equivalent to a mere 5 United States quarters stacked one upon the other, scattered thinly across an entire year. Here, in this desolation that mirrors the Martian surface, researchers like Armando Azua Bustos from the Center of Astrobiology in Spain have made astonishing discoveries. They have found microorganisms, known as endoliths, not on the surface, but clinging to life inside salt rocks, shielded from the sun's harsh ultraviolet radiation and the relentless aridity. These tenacious survivors subsist by feeding on trace amounts of water vapor captured from the air, a perfect, living model for how life might persist in Mars's desiccated subsurface, hiding away from the planet's brutal surface conditions. The existence of extremophiles, organisms thriving in conditions lethal to most life, is by now well documented. Yet, our journey pushes beyond mere tolerance to extreme conditions and asks a more profound, almost philosophical question. Does all life, everywhere in the universe, need what our life needs? To explore this, we turn our gaze to Mono Lake in California, a vast, terminal lake known for its highly unusual chemistry. Its waters are not only 3 times saltier than the ocean, but they are also exceptionally rich in arsenic, a notorious poison to virtually every known organism on Earth. In 2010, a controversial announcement emerged from a National Aeronautics and Space Administration-funded researcher, Felisa Wolf-Simon, claiming the discovery of a bacterium, GFAJ1, that supposedly incorporated arsenic directly into its deoxyribonucleic acid instead of phosphorus, a fundamental building block of life as we know it. While this claim was later heavily debated and largely refuted by the scientific community, it nonetheless served as a powerful, necessary jolt, forcing researchers worldwide to seriously consider the radical possibility of alternative biochemical building blocks, of life based on chemistry alien to our own. The ultimate terrestrial analog for a truly bizarre biology takes us to one of Earth's most hellish landscapes, the Danakil Depression in Ethiopia. This multi-extreme environment is a cauldron of hypersaline, hyperacidic, and high metal content pools, a landscape of bubbling yellow lakes and towering salt formations that look more like an alien planet than any place on Earth. For decades, these pools were considered utterly sterile, too extreme for any form of life to possibly endure. Yet, groundbreaking studies in the late 2010s revealed the impossible: evidence of unique archaea, an ancient group of microorganisms thriving in this caustic brew. Their very presence challenges our most basic assumptions about habitability, hinting at life forms that could survive in conditions that would instantly melt human flesh, in environments where acidity levels hover near 0 on the pH scale, more corrosive than concentrated battery acid. By understanding the absolute limits of terrestrial life, by entertaining the unsettling possibility of a weird life that does not rely on deoxyribonucleic acid or our familiar set of 20 amino acids, we are completely reframing the search on Mars. We are moving beyond the simplistic hunt for liquid water on the surface, which we now know is largely absent. Instead, astrobiologists like Chris McKay at the National Aeronautics and Space Administration advocate for a far more sophisticated approach, searching for subtle chemical imbalances, for unexplained pockets of thermodynamic disequilibrium in the Martian subsurface. These minute anomalies, these unexpected gradients of energy or matter, might be the only discernible signs of a truly alien biology, a faint whisper from a form of life that defies our current definitions, thriving in the ruins of a once vibrant world. The greatest discovery on Mars might not be a familiar microbe, but a complete rewrite of life's fundamental rules. A whisper from the Martian depths, a gas so simple yet so profound, continues to baffle scientists, sending ripples of both hope and frustration across the scientific community. For years, one elusive molecule has offered the most tantalizing, yet frustrating, clue in the modern search for life beyond Earth: methane. This unassuming combination of one carbon atom and four hydrogen atoms holds immense significance because, here on our home planet, over 90% of all atmospheric methane is undeniably produced by biological processes. Think of the vast bubbling swamps teeming with microbes, or the ceaseless digestive systems of grazing animals like cows. They are all constantly exhaling this powerful greenhouse gas, making it a telltale signature of life. The mystery began to unfold in 2004, when the European Space Agency's Mars Express orbiter, diligently circling the red planet, first detected faint, transient plumes of methane in the thin Martian atmosphere. This was a groundbreaking observation, a fleeting hint of something intriguing happening beneath the barren surface. The excitement truly intensified years later, when the National Aeronautics and Space Administration's tenacious Curiosity rover, tirelessly exploring the ancient riverbeds of Gale Crater, intermittently confirmed these detections from the ground. What Curiosity observed was even more astonishing: distinct seasonal spikes in methane concentration, levels that appeared to mysteriously rise during the Martian summer and then equally mysteriously fall back down in the winter months. This was not a steady background hum, but a fluctuating, almost breathing presence, inviting a real-time scientific debate unlike almost any other. The initial electrifying hypothesis, one that captured the imagination of astrobiologists worldwide, suggested a biological origin. Scientists, like the esteemed Sushil Atreya from the University of Michigan, championed the idea that these methane plumes could be the very burps of methanogens. These are ancient, hardy microbes that, if they exist, would likely be living deep underground, thriving in hidden pockets of liquid water that are shielded from the brutal surface radiation and extreme cold. The notion is that their metabolic activity, much like our own biological systems, could ebb and flow with the changing seasons. We can envision how this might work as Martian temperatures rise in the summer, warming the subsurface ever so slightly. It could lead to the temporary opening of tiny, almost imperceptible fissures in the planet's crust, allowing trapped biological gas to seep upwards into the atmosphere. Then, as winter returns, these subterranean pathways might constrict, sealing the gas underground once more. However, science demands rigorous scrutiny, and a second, more conservative hypothesis quickly emerged, proposing a purely geological explanation for the methane's presence. This theory centers on a well-understood process known as serpentinization. This is a common geological reaction on rocky planets where water interacts with olivine-rich rocks, a type of mineral abundant on Mars. During this interaction, hydrogen gas is produced as a byproduct. Once liberated, this hydrogen can then react with carbon dioxide, which makes up 95% of the Martian atmosphere, to create methane. Crucially, this process requires no life whatsoever. It is a straightforward chemical reaction driven by geology. Both hypotheses presented plausible explanations for the observed methane, setting the stage for one of the most compelling scientific puzzles of our time. Yet, the plot thickened, adding a layer of frustrating contradiction to this already complex narrative. In 2016, the European Space Agency introduced a new player to the Martian stage, the Trace Gas Orbiter, or TGO. This sophisticated spacecraft arrived with instruments far more sensitive, by orders of magnitude, than anything sent to Mars before, specifically designed to detect trace gases like methane with unprecedented precision. The expectation was that TGO would definitively confirm the methane plumes and perhaps even map their sources. Paradoxically, and to the profound bewilderment of many scientists, TGO has detected almost no methane in the Martian atmosphere, certainly not the seasonal spikes observed by Curiosity. This glaring discrepancy has ignited an intense, ongoing scientific puzzle that challenges our very understanding of Mars. So, what are we to make of this scientific conundrum? Is Curiosity's instrument, despite its proven track record, somehow faulty or detecting local phenomena that do not extend into the broader atmosphere? Could the methane indeed be produced at ground level, but then rapidly destroyed by ultraviolet radiation or other chemical reactions before it has a chance to rise to TGO's orbital altitude, like a whisper that fades before it can travel across a room? Or, and perhaps most intriguing, are we witnessing a complex geological process that we simply do not yet fully understand, a subtle planetary mechanism that mimics biological signatures in ways we had never considered? This highlights the messy, exhilarating reality of cutting-edge science, where definitive answers are often elusive, and where a single, invisible gas, clinging to the rust-colored landscape of Mars, continues to hold the key to one of humanity's greatest questions. The true nature of this Martian methane, whether it is a biological breath or merely a geological fart, remains a profound mystery, compelling us to look deeper, to question more, and to remain open to possibilities we can barely conceive. For decades, humanity's gaze has been fixed on Mars, driven by an insatiable curiosity. Can we reach it? Can we live there? But as the technological marvels of our age bring us closer to a human journey to the red planet, a far more profound and complex question emerges, one that shifts the very bedrock of our aspirations. Should we? This is not merely a scientific quandary, but a deep ethical and legal challenge, one that could fundamentally redefine our relationship with the cosmos, particularly if the greatest discovery on Mars turns out to be something we never anticipated, something that forbids our presence. Consider the implications. The moment we confirm the existence of even the simplest microbial life on Mars, a planetary protection crisis would instantly ignite. This isn't theoretical. It is a meticulously planned contingency that could halt all future human missions. Our clearest, most successful guide for navigating such an unprecedented challenge comes not from the nascent field of space law, but from the coldest, most isolated continent on Earth, Antarctica. This frozen expanse, a landmass larger than India and China combined, has long served as a unique crucible for international cooperation, a pristine laboratory for understanding how humanity can explore a pristine wilderness without destroying it. In 1959, at the very height of the Cold War, when global tensions were stretched thin by ideological divides and nuclear brinkmanship, 12 nations achieved something extraordinary. They signed the Antarctic Treaty System, an agreement that stands as a stunningly successful model for peaceful international scientific collaboration and environmental preservation. This treaty didn't just demilitarize an entire continent, forbidding any military bases or weapons testing. It also set aside all territorial claims, allowing nations to put aside their flags and disputes for the greater good of scientific discovery. The framework established science as the primary, indeed the only, human activity permitted on this vast, icy land. This historical precedent, born from the depths of Earth's most extreme environment, is the direct philosophical ancestor of our modern space law. Less than a decade later, in 1967, the Outer Space Treaty was forged, echoing Antarctica's principles by declaring celestial bodies as the province of all mankind. This bedrock of international space law enshrines the idea that space is for everyone, not for conquest, but for peaceful exploration. It is this treaty that underpins the critical concept of planetary protection, an international principle rigorously guided by an organization known as CORE, the Committee on Space Research, and meticulously enforced by every major space agency on Earth. The very notion of planetary protection is rooted in a fundamental responsibility to avoid what scientists grimly call forward contamination. This is the irreversible tragedy of introducing Earth microbes to a potentially native Martian ecosystem, effectively destroying it before we even know it is there, before we can even begin to study its unique biology. To counter this existential threat, the protocols for sterilizing spacecraft are incredibly stringent, a process far more meticulous than preparing a surgical instrument for a delicate operation. Engineers and scientists alike, including figures who have held the immense responsibility, like former NASA Planetary Protection Officer Dr. Cassie Conley, have tirelessly worked to establish these protocols. Every component of a rover like Perseverance undergoes an intense baking process, subjected to temperatures exceeding 110 degrees Celsius for hours on end, effectively vaporizing any earthly contaminants down to a microscopic minimum. This meticulous effort is a testament to the scale of the moral dilemma. Imagine the immense effort, the billions of dollars, the collective human ingenuity poured into reaching Mars, only to discover that the very reason we sought it, the presence of life, becomes the reason we cannot fully claim it. This forces us to confront a difficult, almost existential question. If we confirm that life exists on Mars, should the entire planet be declared a planetary park, off-limits to human colonization forever, to preserve its unique biology, its untouched evolutionary path? This profound challenge frames colonization not as a mere technological hurdle to overcome, but as a deep moral test. It forces us to weigh our innate exploratory impulse, that driving force that compels us to reach for new horizons, against our solemn responsibility as potential galactic custodians. It demands that we consider whether the greatest discovery we could ever make on Mars might also be the most unsettling, the very reason we should never truly go there in person. The flickering images of Martian domes and sleek starships, often bathed in the ethereal glow of a computer-generated sunset, have captivated us for decades. These are the glamorous postcards from a future we yearn for, a testament to humanity's boundless ambition. Yet, beneath this romanticized veneer lies a stark, unglamorous reality, a complex web of economic and psychological hurdles that will ultimately define any true attempt at building a city on the red planet. The monumental challenge isn't merely reaching Mars, it is surviving there, not just for days or months, but for years, perhaps even a lifetime. To truly grasp the scale of this undertaking, we must first confront what rocket engineers call the tyranny of the rocket equation, a fundamental law of physics first derived by the visionary Russian rocket pioneer Konstantin Tsiolkovsky in 1903. This mathematical dictator dictates the staggering amount of propellant needed to launch even a small mass into space, let alone across millions of kilometers to another planet. To send a single kilogram of payload from Earth's surface to Mars requires hundreds, sometimes thousands, of kilograms of fuel to overcome Earth's gravity and achieve the necessary escape velocity. This isn't just inefficient. It makes the widely held vision of shipping fully formed habitats, or even a simple cheeseburger, from Earth to Mars an absolute fantasy, an economic impossibility on any meaningful scale. Consider that the cost of launching a single kilogram to low Earth orbit currently hovers around $20,000, and that cost multiplies exponentially when targeting the Martian surface. This prohibitive cost structure instantly elevates self-sufficiency from a distant goal to an immediate, day-one prerequisite for survival. Without the ability to live off the land, any Martian colony would remain an impossibly expensive, perpetually endangered outpost, a glorified camping trip dependent on an umbilical cord stretching across 70 million kilometers of hostile vacuum. This grim reality underscores the critical importance of in situ resource utilization, or ISRU, which is the practice of harvesting and using materials found or manufactured on other celestial bodies. We are witnessing the very first baby steps in this monumental endeavor through current experiments like the Mars Oxygen In Situ Resource Utilization Experiment, known by its acronym MOXIE, aboard the Perseverance rover. This remarkable instrument has successfully generated oxygen from the thin, carbon dioxide-rich Martian atmosphere, proving that the very air of Mars can be turned into a vital resource, a literal breath of fresh air for future human explorers. Beyond the unforgiving economics and the physics of propulsion lies an even more complex, more fragile element: the human mind. The data we collect from Earth's most extreme environments serves as our closest proxy for what prolonged isolation on Mars might entail. Journey to the heart of Antarctica, to places like Concordia Station, a joint French-Italian research facility located deep within the continent, where scientists endure months of complete isolation, perpetual darkness in winter, and temperatures that can plummet to -80 degrees Celsius. Psychological studies from these long-duration stays reveal profound phenomena, perhaps most notably the third quarter effect, a severe and often unexpected dip in morale, motivation, and cognitive function that typically strikes 3/4 of the way through a mission. This isn't just boredom. It is a profound cognitive impact stemming from sensory monotony, the crushing sameness of a confined environment, and the sheer psychological weight of extreme isolation. Astronaut memoirs and data from long stays aboard the International Space Station echo these findings, revealing that the true challenge of a Mars mission isn't the relatively brief 6-month journey there, but the years of living in a confined, lethal environment once you arrive. On Mars, the sky is always a dusty pink, the landscape unchanging save for the occasional dust storm, and Earth is nothing more than a bright, distant star, a pale blue dot in a sea of black, a constant reminder of everything left behind. This reality deconstructs the romantic pioneer narrative, replacing it with a realistic portrait of a Martian colony not as a triumphant frontier settlement, but as a high-tech, high-stress Antarctic research station, albeit one on another planet. Its success will depend far less on heroic individuals and far more on robust supply chains, meticulous resource management, and a deep, empathetic understanding of the inherent frailties of the human mind, which will be stretched to its absolute breaking point. For eons, a silent, rust-colored sentinel has orbited our sun, a stark mirror reflecting our own uncertain destiny. What if the true value of our relentless quest to understand Mars, spanning decades of missions and billions of dollars, isn't found in a definitive answer about life or a blueprint for future colonization, but in the profound, unsettling truths it reveals about our own vibrant, blue home? This red world, scarred by eons of cosmic erosion, stands as a chilling testament to planetary fragility, a cautionary tale whispered across 70 million kilometers of vacuum. We have come to understand Mars not just as another planet, but as a fossil planet. It is a planetary sibling that, billions of years ago, began with strikingly similar ingredients to Earth: abundant liquid water, a thick, protective atmosphere, and vigorous volcanic activity that shaped its nascent surface. Yet, somewhere along its 4.5 billion-year journey, Mars took a dramatically different evolutionary path. Its internal dynamo, once generating a powerful global magnetic field that shielded its atmosphere from the sun's relentless solar wind, sputtered and died. With this shield gone, the solar wind began to sandblast the Martian sky, stripping away its precious blanket of air, leaving behind the desiccated, cold world we observe today. By meticulously studying Mars's demise, through the groundbreaking data streamed back by missions analyzing its lost magnetosphere and its arid, desiccated geology, we are, in essence, performing a cosmic autopsy on a failed Earth. Every rover wheel track, every spectral analysis of its barren rocks, every precise measurement of its vanishing atmosphere provides invaluable insight into the delicate, interconnected planetary scale systems that tirelessly keep our own world alive. This profound perspective transforms Mars from a mere exploration target into a crucial, indispensable laboratory for understanding the universal principles of planetary habitability and, perhaps most critically, the long-term future of Earth's own increasingly vulnerable climate. Now, let us turn this cosmic mirror back upon ourselves. Consider the sheer, unimaginable scale of the technological and societal effort that would be required to make even a minuscule patch of Mars habitable, a theoretical process known as terraforming. Such an endeavor would demand a multi-trillion-dollar investment, an economic and engineering feat dwarfing any human undertaking in recorded history. This serves as the ultimate, most humbling object lesson in the utter irreplaceability of our own planet. The complexity of Earth's biosphere, a self-regulating, living system built over billions of years, provides every service we need to survive: breathable air, fresh water, fertile soil, a stable climate, all for free, without any conscious effort on our part. Thinkers who have dared to conceptualize terraforming, from the visionary Christopher McKay, a planetary scientist at NASA, to the late revered astronomer Carl Sagan, have proposed theoretical concepts ranging from deploying vast orbital mirrors to direct sunlight onto the poles, to unleashing greenhouse gases to melt the polar caps and thicken the atmosphere. Yet, these are not realistic plans for humanity's imminent future. Instead, they function as powerful thought experiments, illustrating with overwhelming clarity the staggering complexity and gargantuan energy required to replicate even a fraction of the services our own biosphere provides effortlessly. The engineering challenge alone would make building every skyscraper and superhighway on Earth seem like a child's building blocks. Ultimately, our deep dive into the red planet concludes not with a definitive answer about whether life truly exists there, nor with a concrete blueprint for how humanity might one day colonize its surface. Instead, we are left with a far more profound, a deeply Sagan-esque reflection. The very act of searching for life on Mars forces us to confront and precisely define what life itself truly is, pushing the boundaries of our understanding beyond our terrestrial biases. The grand, ambitious plan to colonize Mars compels us to confront our deepest societal values, our ethical responsibilities to potential alien ecosystems, and the inherent psychological limits of the human spirit when faced with relentless isolation. And the silent, rusty visage of the planet itself, hanging in the blackness of space, serves as a constant, sobering reminder of the cosmic fragility of our own vibrant blue home. It is a jewel of life, a swirling oasis of water and air, the true, irreplaceable treasure of our solar system,